So let's go back to the initial example that we were using in the previous video, which was the IQ comparison of Mercy College students to that of the population in general. So what we said was we're measuring IQ, so let's put IQ. And we know that the parameters are the population has a mean IQ equaling a 100 with a standard deviation equaling 15. And now as far as our Mercy College sample goes, at Mercy College, we found a sample mean equaling 103 with an N equaling 100, right? We found 100 people, we gave them the IQ test, or maybe we researched it, however we found the information, with a mean of 103. Now, what we're talking about here, we're saying with our initial hypothesis that, well, we suspect that Mercy College students are going to have a higher IQ than the population in general. And as you recall from the previous video, this is a one-tail directional test, upper tail critical. So let's express that out. Well, when we're doing this, we start the writing with the null hypothesis, right? So our hypothesis would say here, we have null, would be mu, and since it's one tail, upper tail critical, and we're dealing with the null, that's going to say that it's less than or equal to 100, which is the comparison point. And let's put our alternative, which is the same as our research hypothesis, which would be the mu is going to be greater than, Mercy College's average is going to be greater than 100. So that would be, and pardon my sloppy handwriting, but that would be the expression of the hypothesis that we're working on. So one tail, upper critical. Seeing now if Mercy College students have a higher IQ than that of the population in general. So we want to see, is there a significant difference between Mercy College's score and the population in general? Now, to assess whether or not there's a significant difference, and we'll talk about how we define significance in a moment, we want to use what's known as a Z statistic. A Z statistic. This is similar to the Z score. However, the Z statistic is used when comparing means. So to indicate this, what we'll do is put Z, and I'll just put a little asterisk here to indicate that we're not talking about a Z score, we're talking about a Z statistic, which then, again, review the video on central limit theorem to understand the means and sampling means. The formula for this, though, is very similar to that of a Z score. So this is going to be X bar minus mu divided by the standard error. So if you look at your Z statistic, X minus mu divided by the standard deviation, the Z statistic is very similar, but we're dealing with sampling means. So it's X bar minus mu divided by the standard error. And again, take a look at the central limit theorem video to review standard error and what that means. But just as a reminder, we'll put the formula up here for standard error. Right, so the standard error equals standard deviation divided by the square root of the sample size. This is the formula that we're going to use to determine if there is a significant difference between our sample mean over here and the population mean that we're pulling from. So let's plug the data in and see what we get for a Z statistic. So let's set it up by just simply plugging it into the formula. I'm going to change the color of the pen. Let's use this. So we're looking at a Z statistic, a Z stat. That's going to equal mu. Oh, I'm sorry, X bar minus mu. So we're talking, let's see, 103 minus the mu of 100. And that's going to be divided by the standard error, right? That's going to be divided by the standard error. And the formula, of course, is over there. And that's standard deviation divided by the square root of n. So let's just plug that in so we can see what it looks like. So divided by 15 divided by the square root of 100. So that's what it looks like plugged in. So let's start by solving for the standard error. So let's put that over here. Standard error. And we know that now is 15 divided by the square root of 100. Okay, so take the square root of 100. So we're talking now 15 divided by 10. And 15 divided by 10 will give us a standard error equaling 1.5. So we can plug that in. So let's continue the formula up here. So now it's 103 minus 100 divided by 1.5. So we'll do the subtraction. So 103 minus 100 is going to give us 3 divided by 1.5. And 3 divided by 1.5 is going to give us 2. So we have a z statistic equaling 2. Now, is that a lot? Well, like a z-score would tell us exactly how far any given x value is from its own mean. The z-statistic is sort of answering the same question. It's telling us where that sample mean falls in the sampling mean distribution. So how far away is it from the mean of means? Well, in order to assess whether a z-score of 2 is far away enough to say its significance, we have to fall back now on probabilities. Now you recall that if you look at a normal distribution, it breaks down not just the proportion of a population underneath that curve, but it also breaks down the probabilities, right? The empirical rule. That's a portion of it, but that's the probability as well because it's out of a whole. And you probably recall that the closer you are to the mean, the higher the probability is of finding something randomly within that range. And the further out on the tails you go, the lower those probabilities become. Now with z-statistics and trying to establish significance, we typically use two different what we call levels of significance. So I'll put that here, levels of significance. A lot of times you'll see that abbreviated sig. That's a G. There's two that are typically used. One of those levels, and these are probability levels, would be a 0.05, and the other is a 0.01 level of significance. So we're talking about, on this side of it, a 5% chance of getting that score, and on this side of it, a 1% chance of getting that particular score. Now, how we look at this and how we position where that 5% or 1% is coming from is based upon whether it's a one-tail or a two-tail test. So let's pull up a normal distribution and take a look at where those probabilities are going to lie. Now, as we've already talked about, if we're dealing with a one-tail, upper tail critical, we're assessing that the information and the significance level is going to have to be up in this area, up in here. All right, so that's where we're looking. That's where our research or our alternative hypothesis is seeing if things are in this particular range, where everything else coming down on this side falls into the realm of the null. Now, we have to take a look at a couple things. If we're setting our probability levels, and we're talking about it being at 0.05 or 0.01, 5% or 1% chance. What we're looking at is we're trying to see is if there is less than a 5% chance that this is going to happen, or we should get these differences, or less than a 1% chance that we get those differences. So if we're going to set this up, I'm going to draw this a little above. Let's say we're going to put this here. And we're going to put 5%. 5%. That's going to put the critical value of our Z statistic in this range here, which would mean that if 5% to the tail, the upper tail, that would give us 95% in this direction. And if we're talking about a 1%, let's say we have 1%, 1% to the tail, that puts 99% in the other direction. So as long as we're in, if we set the probabilities at 1%, so if we're talking about, right here, 1% is the probabilities, we're talking about a result or a difference between our sample mean and the mean of means of a 1% chance of getting that score, 1% to the tail. That leaves us 99% within the range of what would be the null hypothesis. And with 5%, if we're talking 5% over here, that gives us a 5% chance of finding a difference like that at random to the null hypothesis area for a 95% chance. Now the level of significance, the 5% or the 1%, that's referred to as alpha. That's the best I can draw that for, so you're going to have to live with it. So if you have an alpha level of 5% or an alpha level of 1%. Now let's start with alpha level of 5%. The 95%, well, that's beta. Okay, so if you have an alpha level of 5%, the 95% is beta. So let's draw that in here. And again, this is not going to be something I'm too good at drawing. We have our beta level at 95%. If our alpha level here is 1%, that means our beta level is 99%. So that's what it looks like for a one-tail upper. So I'll just write that here on the bottom. One tail, comma there, upper. So the red is one tail upper. Now let's change the color of the ink. Let's go with a darker green. Now let's say we're going to do with a darker green, we're going to go a one tail lower. These values are still going to be the same, right? The probabilities aren't going to change. So you're still dealing with a one tail lower, you're still dealing with 0.05 or 0.01 with a Z statistic. Except now, one tail lower, we're looking at this range down here. So if we put let's say here, the alpha level, let's say our alpha level is here, and the alpha is 5%, or the level of significance is 5% in this direction because it's lower. That puts the beta of 95% in this direction. All right, so we have our beta of 95% in this direction. And if we're going to go, let's say, with a lower or a less probable alpha level, let's say the alpha level we set is, let's say, the alpha of 1%, right? Because that's the other option that we have. We're talking about 1% to the tail. That puts our beta of 99% going that direction. Oops, let's finish that out there. And our beta of 99%. So really the difference comes down to is which side, one tail upper or one tail lower, which side of the graph we're concerned with. And that kind of fits with the hypothesis test video part 1. It's just now we're adding not just where the null and the alternative hypotheses are, but what's the percentage, what's the probability rate that we're looking at? Is it less than a 1% chance or less than a 5% chance? And as you know, we spoke of a third type of hypothesis test, we spoke about a two-tail. And I'll write the key down here in sort of this darker blue. The two-tail test. And that's where we're looking really for difference. Maybe here, or it may be here. Either tail will work for us. And those probabilities also play out with the z, 0.05 or 0.01, 5% or 1%. Those hold true with all three of these types under a z statistic. However, it's a little bit different because we're splitting the probability over two tails. So what you don't want to do is you're not, I'll draw this up here. Let's say we're going with an alpha of 5%. It's not, let's say 5% here and 5% here. Right? That wouldn't work because if you have 5% there and 5% on the low end, in between, you actually have 90%. And that's not what we want because that just changed your alpha to 10%. So let's erase that. You have to take these particular things here and we got to divide this 5% over the two tails. So let's go back to this. If we take the 5%, that puts on the upper tail 2.5%, and on the lower tail 2.5%. So our alpha of 5% is split on the low tail and on the high tail, which allows us to have our 95% or the beta remaining the same. Now if you go with a 1%, well, now we're only looking at 0.5% on the lower tail and 0.5%, make that a little neater, on the up, it's a 5.5 on the upper tail. So we've taken our 1% now and we split it on the lower tail and the upper tail, which allows the beta to stay consistent here at 99%. So again, what we're talking about is the probabilities of finding a score that would be significant. Under Z, is it a 5% or less chance or a 1% or less chance? If it's an upper tail, you put the whole 5% or 1% on the upper tail, which we have here in red. If it's the lower tail, you put the whole 5% or 1% on the lower tail. If it's a one tail, lower tail, and we have that illustrated here in green. And then in the blue, we're taking the same probabilities. A 5% chance, well, we're splitting that 5% and putting half of it on the upper tail, half of it on the lower tail. If it's a 1%, we're splitting the 1% and we're putting half of it on the upper tail, half of it on the lower tail. And that's the basic breakdowns of how on a normal distribution these probabilities would look. So what is the Z that you need to hit that significance? Well, fortunately, it's pretty straightforward and consistent. So let's take a look at that. Z statistic levels of significance, or the alpha levels. We have a chart that will show us what the Z statistic has to be based upon the probability level, or the alpha level, that you have set. So let's take a look at this chart. Starting up over here, we have the type of test. Right? So we illustrate the type of test. And if you look underneath there, you're going to see our one tail, upper tail critical, our one tail, lower tail critical, and our two tail test. Now over here you have the level of significance in this section right here. And the two levels that the Z deals with, 0.05 and over here 0.01. Now in each of these you have the Z statistic that is the minimum cutoff, right? The decision rule. If you hit this level under let's say for example under a one tail critical, if you have and it's a 5% probability upper tail, if you have a Z score of 1.65 or further from the mean, further out on the tails, you would have significance at this level. If you set the probability or the level of significance or the decision rule being made at 0.01, well, then the z that you're going to need is 2.30 or further from the mean than 2.30. And if we look at one tail, lower tail critical, well, it's the same basic idea except for the z values would need to be negative. So at 5% or 0.05, you would need a negative 1.65 or further from the mean to have significance. If it's set at 0.01 or at 1%, over here you would need a z-score or a z-statistic of negative 2.33 or further from the mean than that. Now if it's two-tail, and the two-tail in this area here, you're splitting the 5% or the 1% half on each of the tails. So for a 5% two-tail, you would need positive or negative 1.96 or further to have significance on a two-tail at 0.05. If it's at 0.01, you need a positive or negative 2.58 to find significance. Now, what we were looking at in our example, we had Mercy College with a sample mean equaling 103, and we found that the z-statistic, let me fix that, the z-statistic equaled 2 when we calculated it out. Now, we didn't set the level of significance of the alpha level, but let's take a look. It was a one-tail, upper tail critical. So this is the one we're looking at. Now, if we set it at 0.05 with a z-score of 2, we would have significance. If it were set at 1% or 0.01 with a z-score of 2, we would not have significance. Now, you set the level of significance before you go into doing the research. We didn't do that here because I wanted you guys to see that under one level of significance, we would have significance. Under this one, we would not.